Hi, hello. Thank you for attending to this very interesting webinar. Today we will present this forensic engineering, structural failure and design restoration in CivilFEM 2016. Ramal Martin, along me, or Ronald Siat, will be presenting you this webinar. Thank you for attending. We will present these two very famous cases of collapse, and then we will show you the software and some conclusions. Thank you.
Well, today's webinar is about forensic engineering, failure analysis, and design restoration, and how CivilFEM and all CivilFEM capabilities just can be used for these fields. Well, as you know, forensic engineering is the investigation of materials and structures that failed or did not operate as intended. So, well, the purpose of this analysis is investigate and locate the causes of failure, and well, once we have understood the structural behavior, the reason of failure, just to study the restoration to improve the performance of the life of the structure. So we will apply CivilFEM capabilities. It's code and standard verifications and non-linear detailed analysis, advanced non-linear analysis. We will apply those advanced capabilities of CivilFEM in this field.
Yes, the two models we will present you today are very famous. The first one is the Hyatt Regency hotel, what the Walkway collapse. This hotel was located in Kansas City. In this case, there are suspended walkways, connections, supporting the roads, and we will see how was the failure. The second one is the Terminal 2 of the Charles de Gaulle Airport. This roof, is a glass and metal and concrete structure. We will present many models to analyze the failure.
Well, we are starting with the Walkway collapse of Hyatt Regency Hotel. It happened on 17th of July in 1981 in Kansas City. And well, here we have an old picture. We can see here there are two walkways, two lines, one over the other, and the second one is connected to the upper one by some hangers. Here we have on the right other details with these white hangers. And both walkways are hanging from top. The bottom one is hanging the top one, and both from roof. These walkways collapsed onto a tea dance. There was a tea dance party here with more than 1,600 people attending, and this collapse causes the deadliest structural collapse until in the USA until the dramatic of the Twin Towers. Well, just analyzing what happened there, there was we found information that there was original design, and due to the construction difficulties, this original design was modified by this other one. In the original design, we can see there was a continuous hanger line, and from that was hanging the bottom one with a total force of P here, and from the walkway of this level also P. This P is transmitted to the hanger through this nut. So this nut is holding P due to the self weight of the top walkway, plus this one. So the total force that should resist the hanger is 2P here, and for the nuts and the webs of this on the flames of this part is P. But the model was modified, and due to construction difficulties, instead of having a continuous one, it was modified by two different ones. So the problem is that the bottom one is hanging from here, from this part, so this load is applied to the top beam instead of being continuous by the hanger. So in this part, we will have double stresses. So at the beginning, it looks like the reason of the collapse. If we analyze those details in the model, we will see the reasons and the loads that cause the collapse. So, well, first, we will start making a beam model, and we will perform a check and design by code. So we will have an idea of how the design was, if the failure was here about, or any other part of the model was failing. After analyzing the original and as-built situation with the beam model, we will go to a much more detailed model with solid elements instead of beam elements. This is a beam model, and just analyze some detail all these parts of the union of both parts. So, well, if we use the software, here we have the Walkway. See here, this is the original situation with one crossing both, and well, these are beams that form the walkway with concrete. On top we have a load here, superficial load over it due to the people that were on it, and on the second on bottom we have single loads that are due to the second walkway on bottom. So solving the model, we have these two loads, and we have solved two load cases. The first one are these loads without just a single load, and the other ones are majorative loads, and we apply these coefficients 1.35 and 1.5 for self-weight and overloads. For well, depends on the code. These coefficients could vary a little bit, but we are using 1.35 and 1.5. Depends on the codes around that value. And then we have checked by code the model. After solving, we can plot results. First, duty loads, and we are going to analyze results we have. First, let's see an example bending moment. That is end results, and we will plot bending moments on these beams. Here we have. Well, the units are here newtons per meter. They can be modified to kilonewtons per meter. That is a more usual unit, 65. And well, we have two ways of plotting. We can plot it the thickness of the beams. So this is the value of here in the center 67, positive, in the support negative 86. But I think it's easier to see these bending moments loads with a thin option. I'm plotting it. These are the bending moments loads, negative and positives. These are the values we have. And well, we can see we have a small peak of forces here. And well, hopefully we should average the value for a constant variation. We can see we have a small peak here, this connection, and we will analyze also the shear force. Shear force, that is transverse shear force in y direction. Okay, we can see using also kilonewtons, transfer system, we have about 213 kilonewtons of shear force. The shear force we see it's concentrated in this part. So what we can see, we have a big shear force due to this design in those points. Also, we can plot it in USA unions. Well, we can plot in different options, but if It's for the American unions. In kids, it's 40, around 48. Then next steps, we have forces and moments. We can check and design the structure. For checking by code, here we have, at the beginning, we can select different codes. For the structural steel, the first option is the Eurocode 3, but we can select also American codes, Indian codes all over the world. We have a long list of codes, British Standard, Chinese, Indian, well, we have a long list of codes we could use. We have checked it with the Eurocode 3, and here we can load results. For loading results, I check in and design results, I change it, and I'm going to plot this one. The checking types can be done here. Check beams. Here, check or design beams, check steel beams, and depends on the active code. We have different checking types. For the hangers, we should check for tension. For the beams, we can check for bending and shear, or bending and axial shear and force. Also buckling, and well, in this case, also especially shear. After checking shear in this part of the model, these are the results we get. The first results we can plot is total criterion. The total criterion is the ratio between the action and the capacity. So if this ratio shall be less than 1. Well, here we can see that this ratio is less than 1 in all the models. So it means all the beams are verified by the Eurocode. Criterion 0.7, it's the closest to 1, so we can see that in this, and it is in the connection between the hangers and the beams. So what we can see, just analyzing the original design, that the quickest link of this part are these connections, and the margin is not very big. The margin is about 0.26. Okay, let's see what happens with the as-built configuration. We are going to open the next model and as-built configuration. Here, just watching it, it's exactly same model, but here we can see, instead of having a continuous line of hangers, they are dividing one side and the other. So in this part, we will have the biggest stresses problems.
Yeah, there was a structural change in the structure, and we will see what's the consequence of that.
First, the first value we are plotting is the shear force that we saw. That's the most unfavorable load force on the model. And now plotting, we can see that, as we suppose at the beginning, in this part, it was where the most concentration of loads was happening. We plot in kilonewtons. We can see that now we have 478 kilonewtons. Before this situation, we have 213. So now it's more than double the shear stress we have here in this part. So well, we've seen just the shear concentration of the loads is very big, and it has, there was not a big margin. We can check again by code this configuration, and let's see what happened. Just checking on. I've already checked by code. The steps are the same. Check beams here, clicking here, modifying here for shear or for what we would like. Bending plus axial plus shear force, and checking them all together.
Yeah, in this case we use the Eurocode number 3, but as you know, CivilFEM can use any other codes available. The American AISC codes, British, Chinese.
So now if I plot the total criterion of the majority loads, well, we can see now we have values over 1. That is, the capacity is about 65% over the demand is about 64% higher than the capacity. So, those points are located here. So we can see this value, the value here is 1.60, about 65, 60, and this is lower, so well. Here we can see that the weakest part of the structure, and then where the damage could happen first, and the reason of the collapse should be located there. Now, for a better analysis, we should perform a detailed model. The detailed model, well, before going to the detailed model, here we can compare results. We have original design, just the load here, 213, total criterion less than 1, about 0.7, and here 1.6, and well, we can see how load here is increased, and the same with the checking verification. And then the next step is doing a detailed model. This nonlinear detailing analysis will be performed with a solid elements and material plasticity, yielding for steel. Well, we have to say that the previous beam model, we perform a code verification. For this code verification, we apply a coefficient to the loads, increasing them for that safety factor. So we can know this model doesn't fulfill the code specifications, but in that part. But let's, in order to analyze what happened, we are going to apply the real loads we have, not margarine or anything. But we apply the real loads, following the path loads that were applied here, so we can reproduce what it happened in the real model. So now we go to the solid model.
In this case, more elements will be taken into account. We will modify the geometry, of course, but you will see that it's very easy to go from a basic model to a more complicated model here in CivilFEM 2016.
Well, this is the detailed model. It's done with solid elements, and we have modeled the hangers, the nut, and all details. In this case, we have modeled only half of the model. Here in this side, we applied symmetric boundary conditions. Here from top, we are just constraining vertical displacements, and here we are applying a vertical load from the bottom walkway. And then we have applied the loads and solved the model. The load case here, just are the loads, so we said the pressure and loads here, and for solving we have divided into the fraction 0.02. So the final solution will have 50 load steps. The last results we could get was till 18. So it means it stopped with about 40% of the load. The 40% of the load, the model stopped because of the beam was breaking down. If we load that results, first we are going to analyze the deformed shape and the vertical displacement. Set component of displacement, and we plot that result. Well, here we can see we've scaled this maybe too much. I'm going to reduce it a little bit. So we can see here in the model we are having deformed shape here, buckling of the flanks of the bottom, yielding, and well, many problems. Also here on top we can see the other is also suffering some damage. So we can also plot example for Mises stress.
Here we can check the yielding or plastification of the material.
Yes, well, here we can see this for Mises stress. There are some peaks here in the nuts, in the border of the nuts, the stress concentration. So for more clear results, I'm going to remove it and just plot with other scales. And of course, instead of pascals, I will use a more pascals. So here we can see just stress concentration. Here we can see there's also a high stress concentration in the welding of both sections. The section is done by the welding of two channels here. So also we can see this section is suffering a big deformation and cannot support the load that the walkway was having that night. So as analyzing the deformed shape and the pictures from the failure, we can see it's very similar, and we could reproduce the reason of the collapse and the failure that is concentrated in this union. So the design was modified due to construction problems. As it was difficult to have one continuous hanger, this line. So what we are proposing is that if you modify the design, you should have redesigned this union. One possibility to redesign is using some stiffeners in this part. So here we are seeing only half of this, and we have proposed, in example, 3 plates here in the section for giving a stiffener to the whole section as not opening, and also some plates for on flanks and webs on both sides for having a much more stiffener section. Just if we model, if we go to that model and we open, save it, and we open the reparation.
You will see that this structural change was very controversial, because this changing from a single to a double hanger will produce this different change of in stresses.
Well, this is one of the solutions we could have. Well, here you can see there are 3 plates for giving a stiffener to the model. Can remove it, them, and also here other plates. I'm also going to remove this part, and this is the model, and we apply the same loads and solve it until the end. So the model, in the results, we can see that we solve the 15 loads, the 15 load steps. It means it could converge and there was no problem, no collapse in this structure. Let's see if there's any damage. Just loading the last step. First, we are going to plot vertical displacement, set direction. And that is in centimeters. Let me. Well, here you can see it's almost 1 centimeter in the center of the walkway, and here in this part it's not so big because of the hanger. And just we can see also there's no deformed shape here. It keeps together So at least it's not opening like the previously one. Let's see if we got some yielding results. Just equivalent plastic strain. Let's plot equivalent plastic strain and let's see. Well, now in the equivalent plastic strain, we can see we have some yielding. Here we have this value. This value, it's concentrated here around the nut, the bottom nut in these points. Okay, so well, those are there, and we don't know if in the other. Well, yes, it looks like in the other there are also some stresses. If I modify the range for trying to find some other bigger zones, yielding zones, I reduce the yielding. Instead of having of 0.003 for the equivalent plastic strain, I reduce it to 1. So what we can see, yielding is located here around the nut contact, also here with the second cable contact, and that is mainly a compression yielding stress, also some other values here, but just located around the nut due to the compression of the nut with the plate, the bottom plate. So with this design, we can ensure collapse will have not happened, and also we should check if this section fulfills the code checking also by code. So we can also perform a code checking with this new section for this part, this reinforced section. So we will use a beam model again with this repair. Here we can see that we have a new box here for modeling this section with new thickness and well, new configuration. If we load also the results, checking results with the majority loads, let's see if that fulfills stresses, the rest of the model. Well, we can see now the model is about 0.7, under 0.7, so we can see the union configuration, and this one section is enough for not to collapse. Okay, so slides. We've seen that the reason of the collapse of these gateways was the modification of this connection and just adding double stresses in the beam part of the union. Okay. So the next example we are going to see is the Chat de Gaulle Terminal 2 roof collapse.
Yes, well, in this case, you will see here that this structure, this lounge roof, the structure consists of 3 main structural layers: an outer layer made up of plate glass, a middle layer that was composed of a metal support structure, and an inner layer part of the shell that consisted of concrete blocks that supported the metal structure. We will present many models to simulate this structure, and we will see how was the collapse. Here you can see this Terminal 2E, in the new one of the this is the most important airport in Paris. Collapsed in 2004, and it was lucky that there were no deceased people, but it produced many other damage.
Well, for the model, we've done different models. We started with a shell element model with beams. The structural part of this is, as Ronald said, there is inner concrete part, which work together with these trusses with some struts that connect both, giving some stiffness to this part. So well, what we are doing to see is analyze this model. We will start using a shell model, and in the same way we will perform a check and design verification by codes and standards, and we will try to find if there's a lack of reinforcement or any other thing, or the trusses are failing or whatever. And after analyzing, having an idea of what can happen with the check and design verification, we can go to a much more detailed model. First with shell elements. In shell elements we can add nonlinear behavior to compute short and long-term deflections. We will also control the deflections, and finally adding more nonlinearities like material nonlinearities and large displacements. Well, the first model was check and design by code for first for bending plus axial. We considered four different combinations. G is the gravity loads, its self-weight plus the glazed roof that is above, and also wind that was blowing from one side. Also, we have the thermal loads applied on the model. And then we perform these Eurocode 2 combinations that makes a 0.6% of the possible applications of overloads. Just before getting some results, just the model. In the model, there was measured higher deflections, higher than expected. That night, there was a really low temperature outside, minus 20 degrees, and people, it collapsed early in the morning, and people before collapse heard some concrete cracking noise, and also some dust following from this roof. Okay, if we go to the model, just here we can open
we'll start with the simpler case, the linear case with the bait with shells.
Well, as I said before, there's here class over it. So the loads we have, load groups, here is the glazed roof on it. We can apply on the mesh. In similar way, we have wind. The wind is blowing lateral. And the thermal situation. These thermal loads, there was outside the glazed roof, there was minus 20 degrees. Inside, it was around 20 something. And well, performing a thermal analysis, the result was like a gradient on the structure between minus 13 outside and about 4 inside. So it's like a 20 degrees gradient on the model. So well, the load cases we have solved are temperature, gravity loads, and overloads due to wind and permanent loads. These permanent loads combinations are gravity, glazed roof, and gateway. Here, these holes are due to some gateways here for the fingers of the plane. So also we can see the model just clearing the loads. The model is full of some openings, some windows for giving some light inside the terminal. If we open results, here we can see an example, some combinations, forces combinations. I'm going to plot in example the gravity loads just with a coefficient of 1.35 plus wind plus thermal loads. Well, the way to make these combinations is after solving these load cases, we can make the combination here in this window. In here are the combinations that we have already defined. Here we can add a new combination, and this new combination, well, can have different load cases. Here I select them and I apply different coefficients. Whatever. So in this way, we generated the combinations. For this combination, I'm going to plot in example bending moments. Here for the bending moments and also reinforcement amount directions, we can see here, if I plot the axis of the model, we can see that the horizontal axis is X and the circumferential axis is Y. So, well, taking that into account, in Y direction and X direction will be the bending moments and reinforcement. So, plotting results, in example, bending moment per unit of length in X direction, in X axis. Well, we can see here we have modified to some more appropriate values, and well, here we can see we have, due to this whole discontinuities, we have some peaks of forces here in these zones, and well, if we plot in the other direction, we can see those loads, and if we plot this bending moments in the other direction, we can see also, well, mainly concentrated on these parts, also near the struts that connect them and on top of the roof. So after making the combinations, we can design by code. For designing by code, design cells, here we can use different options. We can design using the orthogonal direction method in taking into account in plane shear and torsional bending moments. It's very important to take into account in plane shear and torsional bending moments due to these holes and these openings that will generate in plane shear, high in plane shear values. Well, after performing those combinations, we can get here the bending reinforcement envelope and the shear reinforcement envelope. We have to open the bending reinforcement and plot these values, centimeters per meter. I'm going to plot the first reinforcement amount in Y top, in example. We can see, well, the reinforcement amount is located here in this part, the biggest amount we need, and also in this part in Y top. Y top is the outside part, and Y is the circumferential direction. As expected, here on both sides, we need a big amount of reinforcement located especially in these parts due to these holes. If we plot instead of top the bottom part, the bottom of the reinforcement, the top, sorry, and the bottom here. Well, we can see the bottom is concentrated here, this part. Well, first I have to say that we didn't know the reinforcement amount, the exact reinforcement amount this model had. So, well, we have supposed that it was designed, the reinforcement amount that this model had, fulfilled with the code specification. So we used this reinforcement amount we are getting for the nonlinear models. We are using the reinforcement amount we get from the code design. So, well, the next step, for after bending plus axial, we add door reinforcement and continue checking the model. Next check is shear checking. If we perform also the shear checking, this is what we are getting. Shear envelope results here, shear envelope, shear reinforcement envelope, and we are going to plot the area per unit of area of shear reinforcement. Well, CivilFEM, when the model cannot be designed in some points, CivilFEM just mark those elements that cannot be designed with this high value for the user to locate it very fast and just try to understand why. Well, so we can see that the points where the model couldn't be designed are mainly located on the connections between the trusses here and the concrete in those points. So there it couldn't be designed. Let's analyze the reason why it couldn't be designed. One of the results we can plot as well is the maximum design shear force that can be carried without crashing the concrete compression structures. If we plot it, we can see that that value in kilonewtons, in example, is around 1,814 kilonewtons meter in this zone. That is the maximum shear that this section could support, taking into account all the steel. And if we see this is one almost 2,000, but if we plot results of this combination, the forces we have in this combination, we will see in example, this is the combination, the wind plus thermal. If we plot the out of plane shear, transverse shear force per unit in y direction, we can see it's 3,000. It's like double. It was 1,800 in the other, and this is 3,000. It means the actual force we have is much higher than the one we can support in this. Going back to the slides, here we can see these points that were located. In order to understand what's happening here, just explaining how the Eurocode check. This is the model, this is the shear force. So due to the shear force, the shear deformation, we will have two directions with 45 degrees, a compression direction and a tension direction. Reinforcement can be calculated in the tension direction, this direction in C, but also we have to check that compression in the other direction can be carried by concrete. So the reason of the failure is that compression here in this part is too big, so the compression strut is failing. As we saw, due to CivilFEM, in the envelope, CR reinforcement envelope, this is the design maximum design shear force that can be supported by this. So we can add, even if we have many reinforcement, this model cannot be designed because of the concrete failure. The only way to improve it is modifying the connections that will have a much bigger spread of this load, or increasing the thickness. An example, if we increase the thickness in the arc 8, if we perform in the arcade the thickness 245 centimeters and we check the temperature load case, I'm going to load temperature plus wind, this combination. For this part, we will increase thickness to 45. You can see now it's much bigger, so we can try to design it. Results, design cells for out-of-plane shear, and now instead of all the model, we are designing only this arc that we increase the result. Okay, this design. So let's check new result. The new result is this one. Now we can see if we plot reinforcement, we can see now reinforcement is calculated. It means with this new thickness, we will avoid strut problems, compression strut problems. So the only way to avoid that is increasing, the best way to avoid that is increasing the thickness. Well, this is the second problem we located on the structure. First, there are some big holes, many holes here, other big holes that are making a big stresses concentration. The second one, the connection between the concrete and this steel structure is generating a high points in shear and generating points in problems. Here in this plot, after the collapse, we can see there were some of these stress crossing the concrete thickness and appearing in the other side. So the results that we got from the software just match with the collapse data we have. So well, as we saw, we can calculate reinforcement if we increase thickness to about 45 centimeters. Next step is checking, adding non-linearities and checking also the load path we have and deflections. Other data we have from the structure is that there were much higher deflections that we had in the model, that expected. So the measure deflections higher than expected will be with the next model. The next model is linear now, but the only non-linearity we are having is creep and large deflections. Large deflections to take into account second-order effects, and creep to take into account long-term deflection. Here, the load case we are solving is G, time G, but just gravity loads, permanent loads, but for different days, 28 days, the calendar time, 50 days, and so on until 2000 days. In the material model here, what we did is here on creep, setting step-by-step creep. That is the first non-linearity. The next we are doing is adding non-linear crashing behavior, and so on. After solving, we are going to analyze to see the results by one. Well, we will perform a time history plot result, and we are going to see vertical deflection on a point here around what could be 23,881. Result, and well, and we are going to plot vertical displacements. So what we are seeing, we are having first a high vertical displacement above 10 centimeters, and due to creep, that vertical displacement almost reached double, 20 centimeters. If I list those values in centimeters, yes, we can see instantaneous deformity shape. It generates 12.5 centimeters, and taking into account long-term effect, it reaches almost 20 centimeters, which is very, very big. The allowable vertical displacement under all load combinations shall be less than 12.5 centimeters. So we are close to double the allowable deformations. So we can also see that this model, taking into account second order effect, also, well, this is a very thin cell, the thickness is low. Well, we will have also deformation problems. We have found three problems: holes, connections, and high deformations. So, well, the next step is trying to model all them together. Well, the holes are here, the connection problems should be added to creep. So what we saw in the previous model that there were some points where the section couldn't be designed. That is, the compression strut was failing, crashing problems, not cracking, crashing problems in those. So what we will do in the model is simulate the progressive collapse. That is, when a certain load is staying here, in these points, the load that is breaking, what we are doing is deactivating this struts that joins the steel with the concrete, the steel trusses with concrete. So we activate gradually in different steps the ones that reach the load that crush the concrete. If we go to that model,
as you can see from just with only the linear model, we could see all the problems that well at the end produced the crashing. But now with the nonlinear analysis, we can get more accurate results.
Well, this model is very similar to the previous one. We have concrete. The only concrete nonlinearity is creep. We have also large deflections nonlinearity, taking into account second order effects. And also, after solving all these steps till 2000 days for taking into account creep, what we do is in these 3 steps modeling the progressive failure of some of these struts, starting with the first that reach the crashing stresses on concrete and continues with the other one. So we have cancelled, we have deactivated some of these during the solution level in these 3 steps, which are done in the after 2000 days calculation. So if we plot results, these are previous results. I'm going to load the new one. This all, and also I'm going to plot the results in the midpoint of this structure here about, and we can see it's the same number, so we can plot the same values here and plot vertical displacement. So well, here we can see we obtain the same sort of curve, but due to these 3 deactivation steps, we start having a really vertical, curve that is suddenly displacements and very, very fast deformation increase. Well, so we can say now that due to these thermal loads we have that night, the connection between these this steel stiffeners for this concrete layer, those connections failure, maybe concrete cracking and crashing around this, and when that connection starts failing, also due to large deflections, we started having well, this unequilibrium step and collapse of the structure. For having a much more detailed model, instead of cancelling the points where concrete crashed, what we are doing is adding cracking and crashing. So with this model, we start adding as well creep. Instead of cancelling these steel connections, we have cracking and crashing behavior on concrete, cracking and crashing, so it will fail. And in this model, as we have nonlinear concrete behavior, cracking and crashing behavior, we need to set reinforcement. We have set smeared reinforcement, area reinforcement on cells with those nonlinear behaviors, and the loads we have applied is permanent loads for 500 days, and we'll get this curve. And after that, we have applied temperatures on the model and wind loads as well. So we can go to that model.
You can see that activating all these nonlinearity is very easy in CivilFEM. Geometric and material nonlinearities.
Well, here you can see if we go close to the model, we can see there is like some brown lines here and here as well. That is the, not this one, that one, and this other one is the reinforcement is made. And these are cell elements with reinforcement and beams. But now for these cell elements here in the material, we have cracking and crashing behavior. For crashing strains, we will add like 0.75%, 35%, that is a 0.35% of deformity shape. When this deformity shape is reached, the model cracks. Also, we have creep, step-by-step creep. So, well, the load cases we are solving is first permanent loads for 28 days, loads, 28 days, that is, we keep the same loads, the gravity, the weight, and roof, for 50, 100, 500, and after that, 500 days, the next day, 501 day, we will have all loads applied, that is, thermal loads and also wind loads. And we will see as well the vertical displacements of these points. If we plot the results, and let's see the midpoint where to plot them. It's about the nodes in this case is 119, 676. So, and now we are plotting vertical displacements. Well, we can see these vertical displacements are generating a curve similar to the previous one we got, but when applying thermal loads, also we have a vertical displacement. In this case, we didn't cancel anything. We didn't cancel or deactivate any trace of the model as we did before to model that. We just model it with the real concrete nonlinear behavior, cracking, crashing, so these elements have cracked and crashed, and the deformed shape has been increased. If we plot, in this case, vertical, in example, cracking data, we can load loads and cracking data. We can have element results. We can plot crack strains, X component of crack strains. We can see, well, they are located in some zones around these connections, and also bottom, just for seeing it easier, we're going to reduce the scale a little bit. So what we can see, cracking is happening in different zones. This is in X direction, and well, also in Y direction. We are having of crackings in the model.
Yeah, in special all the part which is in connection with the steel structure, you can see that they were in this part, they caused cracking in the concrete layer.
So what we have seen also, we are getting similar values, high deformations due to permanent loads, creep and instantaneous deformations, and when adding these extra temperatures, whatever, concrete cracks, and the connections start failing and increasing the deformity shape. This match also with the pictures that there are from the collapse structure, with these struts that connect the trusses with the concrete, just pointing and just drilling the concrete. Also, people heard cracking sounds and dust falling from top, and also high displacement were measured on the model. Well, the last model we could perform for much more detailed information is a nonlinear material model with large displacement with solid elements, crack and crashing behavior, and instead of smeared reinforcement with bars with the insert features we have. That is modeling trusses here, trusses elements, only tension behavior, and inserting them in the concrete layer. This insertion make them work together as a unique body, and in this way we can perform it similar to what we did with shell elements. We can perform and obtain cracking results and crack data. Well, here we have that model. We can. That model is much heavier. It takes longer time, and well, this is what we have: the reinforcement bars and the concrete and the insertions. So, well, just making a resume of the data that we have. The model problems we found is mainly some holes, lot of holes that just break the continuous of the loads on the model. Also connection problems due to this design of the connections are with a plate inside the concrete. This due to thermal loads and also different loads cracking happen and surrounding at connection loose, so they stop working together, beams and cell. So that is the loss of this connection creates a large deformation and cracking and collapse. Also taking into account these deflections, the design office, the values that gave, it was about 2.8 centimeters, the short-term deflections, and the long-term deflections 5. And the alloy ball value was 12.40. With CivilFEM, the values we got, solving this is about 12, the instantaneous deformations, and the long-term ones about 19. The measure values are very, very close to what we obtained with CivilFEM 10 and 20. And the collapse is obtaining in the similar way when applying thermal and the rest of the loads. When cancelling this connection, collapse happens. Well, if we see just the model, the solid model, we can see here the insertions, those insertions here in the model utils. The insertion, what we are doing is insert in concrete the different trusses we have. Truss number whatever. Here, well, we have many trusses, many values. If we here we have different truss, and truss. Well, just after analyzing this, we have a thickness problem with the concrete for this punchings here. So due to all these problems, the design restoration, the design of the reinforcement, it's very difficult to reinforce this structure because it had last deformation, cracking problems, so it is very damaged, and also this structure, this shape is not working well. Well, in order to avoid these problems, the solution was a new design, this type with trusses above it and just a cover with wood. Similar style, similar look of the terminal, but totally different structure. Trusses for the structure and a light wood holding from that instead of concrete and trusses. And well, summary, we can see here that for forensic engineering, we have a different lot of tools with CivilFEM to be performed. First, we can perform a code checking and design to have an idea of possible lacks of reinforcement amounts, thickness of the concrete shells or beams, also, well, any other type of lack that is very specified in the codes. After analyzing that, very important, a non-linear detailed analysis. We're applying the load paths and obtaining the real situation and the real what it really happened to the structure. Here we can see as the deformity, this part is exactly the same as in the picture we have. Also here we can see the deformity set is increased now in this point where you see it's, well, that is due to the failure of the connection, and where we are having the same sort of collapse and the same sort of results. So well, steps are code checking, then nonlinear intelligent analysis to understand the reason of failure, and then, if possible, restoration of the structure to improve life of the
Okay, thank you very much for this presentation of these real collapsed cases. Well, as you know, CivilFEM always can carry from basic to and simple analysis always to more complicated, and that's our motto. CivilFEM lowers the barriers to nonlinear finite element analysis for structural civil engineering, always with a friendly, easy-to-use graphic in the user interface. So, well, how we can learn this software? We have two ways of learning this CivilFEM 2016. One of the ways is using our international online computer-aided engineering education center, and we have available three courses: introduction, dynamic, and nonlinear analysis. Enrollment is always open every 15 days, so you can register any time. And when the duration of this course is 3 months, and you have more information in our website. Another way, if this part is just practical, but if you want to get to more in depth to the fundamentals, you have the International Masters in Theoretical and Practical Application of Finite Element Method and the Computer-Aided Engineering Simulation. We will start this month our 23rd postgraduate course, organized by InfoCyber and UNED, or Open University, and you can still register because you can enroll this month. If you're interested, there's a new Python programming course. More information here in this website.
Also, well, in our website, CivilFEM.com, you can, if you go to the website, that's here, the website here, you can get first some information about next webinars that we are doing. Next webinar will be about geotechnical materials, and also you can contact to the closer partner. We have different partners all over the world where you can contact them for having more information about the software, and also for having a educational free demo version you can download from here from the website. Just you can use to test the software and just to learn it.
Yes, and always, well, you have available on our social media channels, Facebook, Twitter, YouTube, LinkedIn, and Google+.
Okay, thank you very much for your attention.
Okay.
Bye.
Bye, thank you.